Hey guys, welcome back. Let's get stuck into the types of different multiple linear regressions that are available. Before we do that, I do want to say, in reflecting on what you've done so far in learning about multiple linear regressions in this lecture, it is hard. These are new concepts. They're trying to grapple with what they mean, the assumptions, how to interpret the outputs, the different equations, what the terminology is. So really, a key takeaway I want you to have. Well, firstly, it's okay to be confused, and to keep in mind that to navigate through that confusion, exposure helps a lot. So take a day away from it, from the statistics, and then come back to it, and then read more, rewatch parts of the lectures, anything that you type into Google in relation to multiple linear regression. This is all quite standard in terms of how it's described. So if there's anything you don't understand, you can always search more. But it's really an acknowledgement that there's a lot when you're learning this for the first time. And so keep that in mind, be gentle to yourself, and just keep persevering step by step. Ask yourself at every step, do I understand this? If yes, or if no. If it's no, then it's what don't I understand prior to this? Do I need to brush up on understanding what is variance? Do I understand what I mean by hypothesis testing, or what do I mean by slope and regression, and what are all these concepts and terms? So build your understanding and identify where you don't understand, and I've got some practice questions too to help as well. So that can always be useful, but also you can use AI and develop some practice questions on multiple linear regression, see how you go, and ask it to generate some practice questions when it comes to interpreting outputs of analyses that it creates. So it can create some fictitious analyses for you, generate some output, and you have to interpret what it means. So every 1 unit increase in X shows how many increase in Y, and do it for standardized, unstandardized, lots of different ways in which you can learn. I just want to emphasize that before we dive into the different types of multiple linear regression. So there is standard or direct, simultaneous is what it's called, hierarchical or sequential, and stepwise, which is forward and backward. So let's talk about first the direct or standard multiple linear regression, which is what you've seen so far in this lecture. So all predictors are just entered together at the same time, and it assesses the relationship between all predictor variables and the outcome, which is Y variables simultaneously. It's manual technique and commonly used, and if you're not sure what type of multiple linear regression to use, start with this approach. It's typically the one to go with. So you have a sense of the theoretical rationale for the variables that should relate to your dependent variable and your independent variables, and so you just put them all in the model at once, and you run it to see what the relationships are. Hierarchical is exactly as it sounds. It's actually sequential. So you have independent variables that are entered in blocks or stages. So the researcher defines order of entry for the variables based on theory. So you could enter nuisance variables first to control for them, and then test pure effects of the next block of important variables. So you start with the first block. In this example, it would be, say, on brain health, looking at age, sex, education. And the next one, you account for maybe cardiovascular risk factors, history of smoking, alcohol use. And then the next one, you account for many other factors. Why is this the case, you may be asking? Well, in some cases, it would make sense to put it all into one model. But in other cases, you might be asking the question of, does this model explain more of the variance than the model before it? And so those questions can only be asked through a hierarchical regression. Or the reality in research also is that you may have a model that you think is appropriate, but then someone else comes in, a reviewer of your paper, and says, well, actually, I'd be interested to know what about these factors? Could the results that we see here be accounted for by these other factors? Then you run another model and you see what the effects of those factors are. So that could unintentionally drive you through to the hierarchical regression pathway. So R-squared change is a change in variance of Y explained at each stage of the regression model. And you could do an F-test of the R-squared change. So you could see, is there a significant difference in the change in R-squared between models? So here's an example. Does the number of times a song is played on the radio in the week before the release of the album and the attractiveness of the band explain the variance in the number of record sales in the week after the release of the album, i.e. sales, above and beyond that explained by the amount of money spent on advertisements in the week before the release of the album. So I'm asking the question, in Model 1, we're putting money into advertising to see the effects on the number of sales. Does the attractiveness in the band and the number of plays it has on the radio have an impact on the model over and above just advertisements? And so we can run two models, and they would look like this. We have our first model, which is adverts, and the second model, which has adverts after controlling for airplay and attractiveness. And we see, again, we run an ANOVA to see is there a difference between these models. And in fact, yeah, the second model accounts for more of the variance than the first model in a meaningful way. So it is interpretable, the output. And so when you compare the models, here's what we have in our first model, which we're familiar with and we've digested and looked through before. This 9.612 or 96 records sold for every $100,000 spent. Notice how, in terms of adverts, that figure changes. And so this can happen a lot when you add covariates in that account for more of the variance. It actually reduces the size of the effect that we see for that contribution, because there's variance that's accounted for by these other factors as well. So it's now 0.08. So actually, the interpretation here is for every $100,000 spent on adverts, we have 84 increase in records sold here, because I think it's thousands of records. So 84 increased records sold for every $100,000 spent. So you see that's different from the 96 records sold in this model, because this model accounts for airplay and attractiveness. So for every $100,000 spent, we have 84 records sold after controlling for airplay and attractiveness. Let's have a look at another thing, which is the multiple R squared. Here we have 33% of R squared of variance accounted for in the model. In the model with airplay and attractiveness, we have 66% of variance accounted for in the model. And so these are the key things to take away when we're comparing the model. So the change in R squared is 33%. If advertising accounts for 33.5% of the variation in album sales, attractiveness and radio play account for an additional 33%. So that's quite a big change that we see there in those models. So there's also, so that's hierarchical. There's also forward selection, multiple linear regression, and this is computer driven, so it's a bit controversial because, as you've seen already, much of the statistics that we're using, there's a component of it that is a theoretical rationale. Theoretical rationale for why you're choosing your independent variables, theoretical rationale for the direction as to which you think the independent variables impact the dependent variable. And so when you're doing computer driven, you're just relying on the statistics and not the actual phenomena that's there based on theory. So, but it starts with zero predictors, and the strongest predictor is entered into the model, then the next strongest predictor, until it runs out of significant predictors if they reach criteria. And so the p-value could be 0.05. So it'll just keep adding predictors that are significant until it's not seen, no longer significant, no further predictors. Then you have backward elimination, which is, again, computer-driven, so it's controversial. You have all predictor variables are entered, and then the weakest predictors are removed one by one if they meet the criteria, so p-value greater than 0.05. Now, keep in mind, the p-value and the strength of a predictor are not the same, right? The strength of a predictor is actually the estimate here, which is the size of the effect or that we see in here. And the p-value is just saying, does the slope differ from zero, right? And so that is forward and backward elimination, and you have stepwise multiple linear regression, which is computer driven. Again, it combines forward and backwards. At each step, variables may be entered or removed if they meet certain criteria. It's useful for development of the best prediction equation from a large number of variables, and redundant predictors are removed. So what are situations where these could be used? So in forward, backward, and stepwise, it can be used in situations where you have really large amounts of data and you're trying to get a sense of what variables are related to your outcome variable of interest, or could you develop a model that predicts the outcome variable pretty accurately? And so the model statistically will find a way to minimize the variance through the inclusion of variables. So this can be used in neuroimaging data where you have lots of neuroimaging scans and brain regions, and you're trying to get a sense of how can we best model this in terms of health outcomes, for example, time to dementia diagnosis. In saying that, it's still very controversial because of the fact that you're relying on an arbitrary 0.05 threshold for inclusion or exclusion of variables. When I run models, I will still keep variables in the model, even if it's not statistically significant, if there's sufficient theoretical rationale for it to be included in the model based on previous literature. So the types of multiple linear regression summary is that we have the three main ones. We have standard, which is to assess the impact of all independent variables simultaneously. Hierarchical, to test independent variables in a specific order based on hypothesis derived from theory. So you could ask the question of, does this model account for variance over and above model one, which you couldn't ask in the standard regression model. And stepwise is if the goal is accurate statistical prediction from a large number of variables, it's computer driven. And so you have forward and backwards methods here. So I wanted to show you an example of this in action, how this looks like in a published paper. This is research that I've done that looked at the association between menopausal status and brain volumes to see is there a difference between pre and postmenopausal women, because women have higher rates of dementia than men. And in part, this is because they live longer. And so age is the biggest predictor of dementia. The older you are, the more likely it is. It's not deterministic, but it is more likely that you develop dementia as you get older. And so a question, and we found that women are, researchers found that women are at higher risk of dementia than men. And it's accounted for largely by age, but it doesn't seem to explain all of the variance, right? There's some of this variance that's unexplained. And so people have been interested in, myself included, perhaps we could point to some of the changes that are unique to women or the physiological changes that are occurring and their impact on brain health. And so I focused a lot of my research on menopause and even hormone replacement therapy use and see what the contributions are of these components to brain health. And so this paper was investigating this for menopausal status. I used the large UK Biobank study, which has 500,000 participants, and I looked at women who were premenopausal and postmenopausal, and I conducted some analyses to get a sense as to what is the difference in their brain volume. So just to orientate you, so it's a multiple linear hierarchical regression model. So I did multiple models here to generate estimates for association between menopausal status and brain volume. So the first three models relate to total brain volume, then the next three relate to hippocampal volume, which is the area of the brain first impacted in Alzheimer's disease. And it's where features such as memory or spatial navigation are impacted. And so what I want to show you is a few things that we've learned so far. So first, the dummy coding of variables. So I dummy coded the independent variable to be either the baseline was women with who had not had menopause, so premenopausal women, and then the comparator group was women who had menopause, so postmenopausal women. And this is the change in total brain volume between them. So you can see that postmenopausal women had 16,980. The units is in millimeter cubed. So 16,980 millimeter cubes more total brain volume than premenopausal women. And here's the confidence interval that's there. And this isn't very intuitive, right? The 16,980, unless you're in the neuroimaging space. So I tried to quantify the percentage difference. This is like a standardized measure. So rather than using standard deviations, I use percentage difference here to quantify the difference that we see. And here is age, and I've actually controlled for age in the model, right? And said, so this is showing the estimates from there. What I want to show you is sort of in the ways in which it's reported, right? And so the p-values are here, the confidence intervals are here, and you see the delta R squared that's here, right? So this first model shows that 30% of the variance is accounted for, or 31% of the variance is accounted for. And then the next model accounts for an additional 0.9%, so 1% of the variance. And the next model accounts for very little additional variance that's there. So that's really the key takeaway from that. So we have about 30% of the variance accounted for in these models. So the model 1 is adjusted for age. Age is centered on 45. Remember I said that it doesn't make sense to interpret where x equals 0 if for the intercept if it's not meaningful or interpretable, or if data hasn't been collected. In this study, the UK Biobank study, they included women from 45 years and up. So for me, it didn't make sense to interpret age, where the regression model would extrapolate all the way to 0. You can just move that, so it doesn't change the slope, it just moves where it's centered. So instead of having it go through 0, I actually moved it to have the intercept go through 45, or to center it on 45, so that it starts at this is for every 1 year increase in age after 45, there's a 5,970 millimeter cube decrease in brain volume after controlling for covariates. So that's what that interpretation is. So that's what mean centering does. Doesn't change the slope, just moves it so that it becomes interpretable for your data set. So model 1 is adjusted for age, centered on 45, smoking history, waist circumference, and diabetes history, because we know all of these components are impacted through impact brain health, and also menopausal status. There's changes in waist circumference that can occur as well. Model 2 is additionally adjusted for vascular heart problems, education, physical activity, alcohol use, number of children. Model 3 includes an interaction term, which we'll talk more about in a future lecture about moderation. So, and all estimates are unstandardized at millimeter cubed. So I've explained what that is there. So the first two models, the first model incorporates the relationship between menopausal status and brain volume, accounting for some variables, covariates. The next model accounts for additional covariates. The third model has an interaction term in there. And that's the same structure that you see for the hippocampal volume as well. And so that's the key takeaway. So I guess I wanted to show you what that looks like in a published research. You'll notice that not all of the information is reported, but the critical pieces that I'm teaching you to look at in terms of the models are what's reported in here. So I don't report all of the covariates and their estimates because it would be just too long of a table. And so I've just reported the estimates of interest here, which were menopausal status, noting that I've controlled for these other variables. Excellent. That's the key takeaway, and that's an example of hierarchical regression model in action. So let's talk about comparing the strengths of predictors using 95% confidence intervals. So this is our adverts, airplay, and attractiveness scale example predicting the album sales. In R, to get the standardized estimates, you actually just use the scale around each of the variables, and it standardizes it for you. What I want to show you is that you can actually get a sense of whether there's a significant difference in the strength of predictors in your model by looking at the confidence intervals and whether they overlap or not. So we can see that for the adverts and airplay, the confidence intervals overlap quite tightly. They're pretty much exactly the same. So there's no significant difference in terms of adverts and airplay. But in terms of adverts, airplay, and then attractiveness, which is 0.11 to 0.27, they don't cross. The confidence intervals do not cross. So you could make the conclusion that airplay is significantly larger. There's a significant difference in the size of effect between airplay and attractiveness, whereby airplay is larger in effect size than attractiveness. Same thing with adverts. Adverts is larger in effect size than attractiveness. So that's using the confidence intervals here. And if they don't overlap, you can make conclusions about whether there's likely the size of the effect is larger, statistically significantly larger than the effect in the other variable. So that's the key things when it comes to comparing the strengths of predictors using 95% confidence interval. So from the 95% confidence interval, we can see that adverts and airplay are significantly larger or stronger predictors of sales than attractiveness, given the confidence intervals do not cross over between these variables. This is a really useful tool when you're looking at measures. And you can remember this is only applicable in terms of using the standardized measures. So you can't do it for unstandardized because the confidence intervals are on different scales, only for when you standardize. That's why it's all scale just means standardized. So these are all standardized units. Excellent. So some practice questions. A multiple linear regression is a what type of statistical analysis? Is it univariate, bivariate, or multivariate? hopefully you're saying that the answer is multivariate, right? We have multiple variables in the model, multiple independent variables, looking at that relationship with the dependent variable. The following types of data can be used in a multiple linear regression analysis: interval or higher dependent variable, interval or higher independent variables, dichotomous independent variables, all of the above, or none of the above. What is the answer here? Hopefully you're screaming all of the above. If you got tripped up there, it's likely maybe the dichotomous independent variables, remembering that if an independent variable is coded dichotomously, then it can be included in the multiple linear regression analyses, just as I did here with menopausal status being dichotomously coded as premenopausal or postmenopausal. Yeah, excellent. So that's that one. In multiple linear regression, the square of the multiple correlation coefficient, R squared, is called the coefficient of determination. Yeah, so I couldn't stop myself, sorry. So hopefully you got that one in before me. So it's the coefficient of determination, although big R is sounds cooler, but it's coefficient of determination for R squared. A linear regression produces the equation of y hat equals 0.4x plus 3, which indicates that when y hat equals 0.4, x equals 3, when y hat equals 0, x equals 3, when x equals 3, y hat equals 0.4, when x equals 0, y hat equals 3. Trick for questions like this is just put the numbers in and see what the outcome is. But also, hopefully, you're gravitating to the idea that when x is equal to 0, y hat is equal to 3. So the answer is D. When x is equal to 0, y hat is equal to 3. Excellent. In multiple linear regression, a residual is the difference between the predicted value and the actual y value. Is that true? Hopefully you're saying, of course it's true, right? Remember that beautiful diagram we had with the red line and we had all the dots and we had the actual value which was observed and the error is the difference there, and the residuals, you're calculating the total error. So yeah, you have the predicted value where you think they would be on that line, and then your actual value of where actually the dot is, right? So which types of multiple linear regression would you use for the following? So here are some examples. Does spending time with your friends relate to life satisfaction above and beyond satisfaction with one's job? I want to build a regression equation that can predict life satisfaction based on a number of factors that are significantly related to this variable, though I have no set predictions. And what is the relative importance of hours spent studying, working, sleeping, and with friends on life satisfaction? So the answer is 3, 2, 1. Here. So the first one, I tried to really heavily weight that above and beyond factor in reading out that question, because that should immediately take you to hierarchical regression. We're trying to see, do these factors explain variance and outcome measure over and above the initial model? The second one is there's no set predictions, and they're trying to build a regression model that predicts life satisfaction based on a number of factors, so it's stepwise. And the third one is just what we're used to in terms of a normal question. So what is the relative importance of hours spent studying, working, sleeping, and with friends on life satisfaction? So there's no difference in terms of the amount of variance accounted for in the model. There's no sense of trying to predict using significance testing and having no set predictions. So it's a direct standard regression, just your normal regression that's there. Okay, excellent. So those are the practice questions. Hopefully that's a good sort of litmus check of your understanding of some of the regression concepts. What I want to do now is sort of blow your mind, if you let me, which is about sort of seeing the relationships of variables. When I was an undergraduate student, I really struggled with statistics. I only started being able to understand statistics when I started my PhD, and I started teaching myself statistics, using books such as Andy Field's book, which I reference here because I think it's quite useful in terms of the examples and the data provided. But when I started teaching myself statistics, I learned two things. One is that statistics is filled with amazing stories, right? There's all these great examples of why these statistical tests came to be, and I think it's beautiful. And you've heard some of them already in terms of, let's say, for example, T-Test with the Guinness Brewery Factory and how they looked at the quality of beer in two different batches. So he created t-test, and he called it Students T because the Guinness, his manager didn't want him to actually release that to the world. And so he did it under the pseudonym Students, so it's Students T-test. And you learn all these amazing stories. And the second thing I learned when learning statistics is actually there's so much interrelationship between so many different concepts. And the reasons are very interesting. In large fact, there are some big figures in statistics who were feuding with one another, and it caused a lot of divergence in ideas. So that resulted in different terminology, different frameworks and ways of thinking for things that could be integrated into a single framework. And it was when I was learning more about this, I realized that the linear models framework or generalized linear models can be used to think about many of the statistics that you know about already, and they're all actually interrelated. So when I say generalized linear models, this encapsulates things like correlation, simple linear regression, multiple linear regression. You may hear things words like mixed effects models or logistic regression models beyond this course when you're reading papers. All of these are in families of generalized linear models. And what this person does, Jonas Lindevolf, he did this great diagrammatic example of showing how common statistical tests are linear models. So here's the first example showing y is independent of x. You have a one sample t-test or a Wilcoxon signed ranked test, and this is how to run it in R, and this is how to do the linear model in R. And is it exact? And it shows you in cases where it's exact or when you need a certain sample size threshold for the results to be exact. And it tells you the linear model in words. So one number, intercept, i.e. the mean, predicts y. And this is the graphical relationship of what that is. And it goes on for each of these different, so it shows you how Pearson's correlation, which we've covered already, can be done through core-test, or Spearman's correlation, which is using core-test and R, can be run like a linear regression model, which we've seen already in this course. So I've showed you how Pearson's correlation is like a linear regression model, and here's an example of how to run Spearman's correlation in R, and it shows you that there. It goes on showing ANOVAs and how ANOVAs can be run like linear regression models, and ANCOVAs, one-way, two-way ANCOVAs, and how that can be run using the LM linear regression models, and the conditions for, and then even chi-square tests. So I just wanted to really show you the relationships between all these components. If you're in disbelief and you don't believe me, here's a nice little example that I put together just to demonstrate the first one. So this is looking at t-tests. And so here is some R code which you can copy and run in R, and you'll be able to generate the same answers as I have. I've set the seed. What this means is the data starts, because I've simulated the data, it starts from 7126, so it's reproducible. You could set the seed at any number. It just is where it starts sampling from. So every time you sample, you get the same results. So I just put 7126 because that's the course code. So simulate data. So I've created a variable, which is a factor, a categorical variable with a control and treatment group of 50 participants. And then I created a variable that which has a normal distribution for 50 participants with a mean of 50, standard deviation of 10, and then 50 participants, mean of 75, standard deviation of 10. And then I want to put this data all together into a data frame, so combine G and Y. And you can look at that data frame there. And so I've assigned each of these to G, Y, and D as the data frame. And so here is my linear regression model. Here is my two-sample t-test. And what I want you to see is a few things. One is that in the t-test, which compares the means of these two groups, the control and treatment group that I've made up, but just numbers, but it still shows the difference between them. It says the mean in group of the control is 53, the mean in group of the treatment is 72, and the difference is statistically significant between those groups. So you could think of any example, the time it takes to run 100 meters, is that fast or too slow? Run a kilometer? I don't know. Run whatever distance. The controls given nothing, and the treatment groups given a lot of training as to how to run. And we see the difference, and you see it's statistically significant. So there's a significant difference between these means. If in our linear regression model, which hopefully you're now very familiar with now, you're looking at the formula, you're looking at, oh, it's normally distributed because the numbers are quite similar across there. And I knew it was normally distributed because I've simulated from the R norm is through a normal distribution. And here's the intercept and the treatment. Now, in this case, because it's a dichotomous variable, as in control and treatment, R has assigned the intercept to be the control group. So it's just a comparison between the dichotomous variables. So here, the control group is 53.024, and it's the intercept because it starts with C instead of T. So it just did it alphabetically. But you could easily flip that around by doing dummy coding and changing it. But if you're interested in the comparison of treatment to the control group, it says the treatment group had a 19.33 increase than the control group. So this is 53.024 intercept, which is control group, and here it's 53.024. Here, the difference, it shows you the difference, which is 19.33. If you add that to the control group, you'll get 72.35. So these numbers are exactly the same as these numbers. And the p-value that you see here as to that difference, that's the exact same as this p-value here. So it's exactly the same thing, but it's taught through different lenses. And so I just really think it's important to see the interrelationship between linear models and many of the statistics that you learn. And here's an example of how it can work in t-tests when you have a categorical variable for your independent variable for your linear model. So that's the key takeaway there. So hopefully that's blown your mind and given you an appreciation of the interrelationship of statistics. Okay, let's go through what we've talked about in terms of the summary of steps for multiple linear regression models. General steps is you first have the theoretical rationale, so you draw a visual path, or a path or a Venn diagram, and state a research question and a hypothesis. You check your assumptions, you choose the type of multiple linear regression that you want to do, you interpret your output, and then you develop a regression equation. So I've shown you examples of how to go through each of these step by step, several examples of how to do these general steps. And the linear regression is the best fitting straight line for the scatter plot of two variables. We have this formula, which is y equals b of x plus a plus e, which is your error term. A is where it intercepts the y-axis, and b is our slope, x is our independent variable, y is our dependent variable, or predictor and outcome, depending on which terminology you use. Least squares criterion is the line of best fit, minimizes the total sum of squares of vertical deviations for each case. The main takeaway is the least squares criterion is which line fits the data points the best to minimize the error as much as possible. And then we have the ANOVA tests in our models to see, is this line better than the average? Residuals are the vertical distance between the actual and predicted values. We have the assumptions, which is the level of measurement of what it needs to be. Remembering it can be a categorical measure as well in regression. We just have to dummy code it if needed, if you're using some software, or others you don't need to. Sample size, we had some thresholds that were there: normality, linearity, normality of residuals, linearity, homoscedasticity. We talked about multicollinearity, and the residuals are normally distributed. And note check for outliers, including multivariate outliers when we talk about Cook's distance and Mahalanobis distance. Level of measurement, dependent variable can be continuous, it has to be continuous, interval ratio. Independent variable can be continuous or dichotomous. And we saw examples of that. If neither, may need to recode into a dichotomous variable or create dummy variables. We talked about multiple linear regression, the output, the overall fit through R squared, and also what R means as well, the capital R in relation to multiple linear regression models, and the adjusted R squared, which really is related to the population level, but also accounts for the number of predictors in your model, and how we have to ensure that we're using adjusted R squared, particularly when we have low sample sizes. The F and the P values as well of our ANOVA tests, which are comparing the fit of the model. The coefficients, relation between each independent variable and the dependent variable after adjusting for the other independent variables. That's key, right? The interpretation we've seen changes based on the covariates you include in your model. In the adverts example, we saw how that effect reduced when we adjusted for other variables. And so we have our unstandardized estimate, our standardized estimate, t-value and p-value, and I showed you the relationship between the unstandardized estimate, your standard error, and your t-value, which allows you to derive your p-value. So again, the links between all of these components. A regression equation you can write out if useful, and this is where if you have no error in your model, in your population, and then this is your typical model that you have with some level of unexplained error. So the types of multiple linear regression, we talked about standard or direct, which is simultaneous, hierarchical or sequential, stepwise, which is forward and backward in there. And that's it for today. So next week, we're going to talk about multiple linear regression part 2. So we're going to review some of the multiple linear regression 1, semi-partial correlations, residual analysis, interactions, which you saw that term today. We'll talk about it more next lecture, and analysis of change. That's the main takeaway. A lot to take in for today, but once you master multiple linear regression analyses, it'll pay dividends in how you learn about research, how you read research papers, how you understand the estimates that are there, and also how you conduct your own research. So it could be a really critical tool. You can go forth and ask your own questions of interest. So a very useful statistical tool. Saying that, that's it for today. Have a lovely day, lovely week. I'll see you guys in the next video. Thanks, guys.